COVID phylogenetic visualization with mutation time inference and ancestral reconstruction by Mark, Jack, and Yash.
So for background, genomic surveillance enables researchers to track the spread and evolution of pathogens. Nextgen provides real-time visualization of SARS-CoV-2 mutations using global data to display when and where new variants diverge.
So some of our main motivations were just visualizing uh, COVID mutations with internal node time. So providing that time-based information makes a more compelling visualization that also can have more insights. And the secondary motivation was existing time-based methods for ancestral reconstruction lack global temporal coherence, so monotonic kind of relationship. So they're less meaningful in time-based visualizations. So uh, our goals are to produce a meaningful time-based visualization that shows the proliferation of COVID-19. But we also want to kind of bridge this gap between ancestral reconstruction and global temporal coherence.
So the first approach is an overview of our pipeline. We take the entire genome data set, we do the MSA, and then we build the topology based on the date of the tips, the terminal taxa, and then we get the phylogeny, we input it into the ancestral reconstruction, and we parse the final result, do the time scaling, and then take that output to do the final visualization. So for data set, we have two small data sets that's just for testing the phylogeny tree building. And as you can see, if we have outgroup, then the tree is going to be rooted, and then we have correct relative time relationship between the tips. And then we also have a 15 sequences as a toy data set and 120 sequences as a full data set. And these are the tools for MSA that we're using. For phylogenetic tree and ancestral reconstruction, we tried out neighbor joining, but it's not working well. And then we think it may be because we're not considering the evolutionary rate. So we put in the K80 and gamma correction in order to fix it, but it still doesn't work well. So eventually we go for Beast, which is a time-based constrained tree building tool. And then we take that final output and put it into the ancestral reconstruction tool, RASP, with all these parameters that you're currently looking at, and it works pretty well.
Okay, so we have a few different approaches for the actual time scaling step of our pipeline. So our first approach is we're just directly interpreting the output of Beast, because Beast gives you branch lengths that represent a unit of time in years. So we're just kind of normalizing our time representation, and then we can crawl backwards and use that. Our second two approaches use our own optimization method. So the first, we're kind of mixing with Beast a little bit, so it's our hybrid approach. So we're preserving some of the signal from Beast. In our least squares approach, we're just tossing all of the data from Beast, and we're just going straight at it with the topology only as a set of constraints.
Our approach to visualization was we wanted to combine like two like really good tools that we like. We wanted to mimic the way that interactive tree of life generates phylogenetic trees, as well as mimicking how NextBrain shows geographic distribution of samples using like map-based like graphics.
So for findings, as I mentioned before, if we don't have an outgrouped, the tree is unrooted. So the relative time relationship between the tips are not correct. But if you put an outgroup, the time axis begins at the root and progress towards the tips as shown in the graph.
Okay, so yeah, as Mark was talking about before, with our previous methods, we just found that as a result, so constructing a phylogeny without considering time from our terminal taxa just results in a very poor topology that's just kind of incompatible with time-based interpretations. So that's what motivated these. And then as for our objective function, kind of our measure of temporal global coherence, that's based off the relationship between internal nodes and branch lengths. So we're trying to optimize that with our different strategies. And what we found from our time scaling results with this objective function is that our hybrid approach actually performed the best.
And then our findings for the visualization is here's just a screenshot of the visualization tool that we made that allows you to like load in a custom new tree file with the time scaled lengths, and then it generates the phylogenetic tree as shown above, and then below it shows where the mutations occur on the map. if you guys want to play around with this, here's a QR code that you can scan. It'll take you to a website with the tool on it. And here we have a brief just recording of the tool.
Okay, so we had a few different findings for our conclusion. So a big part of it was we need to factor in time into our ancestral reconstruction for time-based interpretation, and our hybrid approach for time scaling actually performed the best. So just preserving that signal from Beast, but feeding into our own optimization method actually performed the best.
And some future works that we want to do is include additional mutations to construct a more comprehensive tree, as well as we want to see geographically diverse mutations to address like the bias that our dataset had to Western nations.
And this reference. Thank you very much. This is our presentation.